Today we're going to talk about the difference between displacement and total distance traveled. So if I have this little bug and he's walking along on this rope, which just happens to be a number line. So he starts at 0 and he walks up to 6. And then he turns around and he walks backwards down to -5. Then he walks back to 0. So if we trace out what he just did, he started at 0, he walked to 6, he walked back to -5, then he returned to 0. Or if we were going to graph this as a graph of position versus time, then this would look like he starts at 0, he goes up to 6, then he goes down to -5, then he returns to 0. So when we're doing a position versus time graph, S of t, we're really talking about position along a straight line like this. And we can even draw this bug's velocity graph, v of t. We know that he was moving forward for a while, then he moved backwards for a while, then he moved forward again. So there's his velocity graph, v of t. We also know that he ended up back where he started, so we know that the area under the velocity curve where he's going forward, the distance he goes forward, is going to equal the area under the velocity curve backwards, the distance he went backwards. If we wanted to know the total distance that he traveled, we would want to actually add up these real areas. And so what we would do is, instead of drawing the velocity curve, we would draw the absolute value of the velocity curve. So it would look just like velocity when it's positive, but when velocity is negative, you would get the absolute value, the positive version of it. So you now have all positive area. And if you looked at all of that positive area, so you added the distance he went forward to the distance he goes backwards, that would give you the total distance traveled. In this case, it's a lot easier to do just based on how far he goes. So we know that he goes from 0 to 6. So notice we're subtracting the position 6 minus 0, or if we don't want to have to worry about what order they're in, let's say we take his original position, 0, and we subtract 6 from it, and we'll take the absolute value of that to make sure we have a positive number. So we take the position at the beginning, and then the position when he turns around, which would be a critical point, a place where the velocity is 0, and then we add to that the distance he goes from that critical point to the next time he turns around, the next critical point. So this time the position is -5. 6 minus the -5. We'll put absolute values on that one too, just so we don't have to worry about whether it's positive or negative. So that's giving us 11. He goes backwards 11. And then he goes from -5 to 0. So we'll say -5 minus 0. The absolute value of that is 5. And we'll add those together. So we'll have 6 plus 11 plus 5, which is going to be 22. So even though his displacement is 0, he ends up exactly where he starts. He traveled a distance of 22 units. So this means that if we're given just a velocity curve, we actually can find both the displacement and the total distance traveled. So here we have a velocity curve of x cubed minus 8x squared plus 15x. We know the displacement, how far he was from when he started here at 0, 0 to where he ends when t is 6, wherever that is. We know that displacement is the integral from 0 to 6 of x cubed minus 8x squared plus 15x. Or that this is the same as the net area under the velocity curve. So what we're going to get when we integrate this, x to the 4th over 4 minus 8x cubed over 3 plus 15x squared over 2, evaluated from 0 to 6. Whatever this number is, this is going to be how far he is from where he started. So we get that the displacement is 18. He's 18 units away from where he started. Since he started at 0, 0, Well, I guess we don't even know that. We know the velocity was 0 when he started. We know he started not moving and started speeding up, but we don't really know what the position was when he started. But wherever he started at, he is now 18 units away. The distance traveled, though, is a little bit more complicated. Remember, we found displacement by taking the integral of the velocity. But to find distance traveled, we need to find the integral of the absolute value of the velocity function. So we need to find the integral of the absolute value of x cubed minus 8x squared plus 15x. Now we don't know how to take the integral of an absolute value. So the only way we can actually find this integral is by finding out what the function is equal to without an absolute value. Remember, absolute values are piecewise functions. Whenever the function is positive, it just gives back itself. But when the function is negative, the absolute value is giving you a negative function. So how do we deal with this? Well, we need to find every place where this velocity function could change signs. So that would be where it equals 0 or is undefined. It's a polynomial, so it's never undefined. So we just need to find out where it equals 0. So if we factor this, pull out an x times x squared minus 8x plus 15 equals 0, which means that x times x minus 3 times x minus 5 equals 0, which means that x equals 0, x equals 3, and x equals 5 are critical points of the position function, or places where the velocity function might change sign. So what this means is that we need to split up our integral at each of these critical points. So we need to do the integral from 0 to 3 of the absolute value of x cubed minus 8x squared plus 15x, plus the integral from 3 to 5 of the absolute value of x cubed minus 8x squared plus 15x, plus the integral from 5 to 6 of the absolute value of x cubed minus 8x squared plus 15x. So now you might be thinking, well, we haven't really done anything because we still have absolute values in all of these. But since we know now that from 0 to 3, x cubed minus 8x squared plus 15x has the same sign, we know that this is either the integral of x cubed minus 8x squared plus 15x, or it's the integral of negative of that. And we know that since we're trying to find total distance traveled, we're going to want the positive value. So we can just switch this to be the absolute value of the integral from 0 to 3 of x cubed minus 8x squared plus 15x dx. And the same argument holds for the other integrals. We can do the absolute value of the integral instead of the integral of the absolute value. Now this only works because we know that our function has the same sign for the entire region. So now we can find all of these integrals. We're going to be finding the integral, which was x to the 4th over 4 minus 8x cubed over 3 plus 15x squared over 2. We know that that is an antiderivative of our velocity. We don't know if it's exactly the position function because we don't know what the plus c would be. But we're essentially finding what could be a position function if it started at a position of 0. And we're evaluating that from 0 to 3 in absolute values, plus, again in absolute values, the same function, but this time from 3 to 5 in absolute values. And then finally, in absolute values, the same function again from 5 to 6, since we want the total distance traveled from 0 to 6. So if I just call this function right here, let's call this f of x. Note what we have here. We have the absolute value of f of 3 minus f of 0 plus the absolute value of f of 5 minus f of 3 plus the absolute value of f of 6 minus f of 5. And this f of x, since it's an antiderivative of our velocity function, and our position function is also an antiderivative of our velocity function, then f of x can only differ from our position function by a constant c. So if we were to subtract two f of x's, that's exactly the same as subtracting two position functions, because the c's are going to cancel out. So it turns out that finding the total distance traveled is the same as finding the change in the distance functions, their absolute values, where you find this change in the distance, the displacement, how far the function has moved from one point to another, on intervals where the object is all moving in the same direction. This is exactly what we did back here with the bug. But now we don't even know the position function, and we're still able to do the same thing. So if we go back to our equation here, where we need to plug in all the points, and we pull out our handy-dandy calculator and plug them all in, we're going to get, for the first interval from 0 to 3, we're going to get 15.75 plus, in fact, we should say we're going to get the absolute value of 15.75 plus the absolute value of negative 5 1/3 plus the absolute value of 91/12. So what this is telling us is that our function, whatever it was, whatever our object was, it moved forward 15.75, and then it moved backward negative 5 1/3, and then it moved forward 91/12. So when we just take the integral from 0 up to 6, we are adding the two positive areas, 15.75 and 91/12, and subtracting off the negative area, the negative 5 1/3. But if we want the total distance traveled, we need to make all of these positive numbers. So we're going to add them all up. 15.75 plus 5 1/3 plus 91/12, which gives us a total distance traveled of 28 2/3 units. And if we look in the graph up here of our velocity function, we can now see this is our 15.75, this is our negative 5 1/3, and this is our 91/12. So if we add them all up, the positive values, the total distance was 28 2/3. But if we look for just the displacement, how far is it from where it started? The answer to that is 18. So to summarize what we've done, if you want to find the total distance traveled, you're looking for the integral from a to b with the absolute value of the velocity function. You can find this by splitting up the integral every time the velocity function might change signs. Then you find each of these individual integrals. These correspond to the areas either above or below the x-axis. You take their absolute values and you add them all up. This gives you the total area, not the net area, the actual total area, which gives you the actual distance traveled. And notice that we said that each of these integrals of the absolute value are actually the displacement between each of the critical points. So it's how far you've gone in one direction plus how far you've gone in the backwards plus how far you've gone forwards again, which is exactly what we would expect our total distance traveled to be. And that this relationship here that goes from the integral to this difference in positions is exactly the fundamental theorem of calculus.